Sorry. Okay. Yeah. So I would like today to finish what I started explaining, and I was much slower than I hoped, but this means just that I will need to cheat a little bit today. The goal remains the same. So on the first day, I tried to explain what I mean by TQFTs and extended TQFTs for this series of talks at least. And I tried to motivate why I would spend most of the time during these three talks talking about a very special construction of a TQFT defined on some sort of not so standard category of coordinates. I introduced it on Monday. I tried to motivate why it's interesting. On Tuesday, I explained how a very special universal object that you have in every finite ribbon category called the n of a certain functor, how this object has properties that naturally allow you to define a functor from most of this bizarre category of cobordisms to finite ribbon category you're considering using this object called the n. Today, I would like to explain how to extend this to a functor, braided monoidal functor on the whole category of cobordisms of Crane and Yetter. And then I will try to sketch a strategy for extending this to a 3 to 1 dimensional TQFT, to an extended TQFT in dimension 3, by cheating, because I don't have time to tell you how to really do this. And sorry about this. But anyway, so today I will start by giving the definition that, so the conditions that you need in order to be able to define these TQFTs. We said that with a finite ribbon category, you can always get a functor from the category of top tangles in handle bodies, which are special curvy tangles in handle bodies, those that do not have closed components. They correspond basically to those cobordisms that have been embedded inside R3, inside the three-dimensional space. So you don't perform surgery on them, and you see them as directly embedded. This is a subcategory. But under certain hypotheses, you can extend the construction to the whole category. You need C to be a braided monoidal category. Okay, we say, let's to say what is the condition. I need some terminology. We say that an object in a braided monoidal category. So monoidal means you can do tensor products. Braided means you have an isomorphism, which is natural between tensor products and opposite ones. And an object, we say it's transparent if, well, if you have this. Have this for every x, for every, sorry, y. Okay, y, for every y in your category. So if for every object in the category, the double braiding with x is trivial, we say x is transparent. The terminology comes from this graphical representation of braiding, of the braiding, because if x is transparent, it means that things can pass through. And so finite ribbon categories can be used to define the whole TQFT if they satisfy the following property, if they are factorizable. So C is factorizable. If every transparent object is of the following form. It's trivial. It's just isomorphic to a finite direct sum of tensor units. The tensor unit is always transparent, and so direct sums of copies of the tensor unit are always transparent objects. And if these are the only ones, then the category is said to be factorizable. And you can think about this as a non-degeneracy condition for the braiding. So the braiding of a category is non-degenerate if there are no non-trivial transparent objects. In a symmetric category, which is kind of the opposite side of the spectrum, every object is transparent. And here we are kind of in the case, which is really at the opposite end of the spectrum. So a modular category which is typically called the modular tensor category also. At this conference, we heard this term many times. It's a factorizable ribbon category. Maybe I didn't say this, let's say finite. It's a factor, C was taken to be finite from the beginning, so it's linear, and it's equivalent to, as a linear category, to the category of finite dimensional modules over some finite dimensional algebra. Okay, and we say a finite ribbon category is factorizable if its Muger center is trivial, so if its transparent objects are all trivial. And okay, like there is a definition that dates back to the beginning of the 90s due to Turayev of what is a modular category, and that one is always required semi-simplicity. This is a generalization of that definition that does not ask C to be semi-simple. And in case C is semi-simple, this definition coincides with the one given by Turayev. So let me write this example. If C is semi-simple, so I said I had, so on Tuesday I said I had two recurring examples. It's semi-simple categories and categories of representations of a ribbon Hopf algebra. If C is semi-simple, then C is modular. It's a semi-simple finite ribbon category. Okay, let's say C is finite ribbon. Okay, and if C is semi-simple, then C is modular if and only if Turayev's condition holds, which is the determinant of the matrix you get from by looking at Hopf links. Yes. Is non-zero if this matrix is invertible. And okay, I recall that this was on Tuesday, so I don't know. But for a semi-simple category, I called I used the letter I to denote the indexing set for a set of representative of isomorphism classes of simple objects in the category. And Penrose diagrams for ribbon categories allow you to interpret this as an endomorphism of the tensor unit, so scalar, for every choice of xi and xj. These are entries in a matrix with I rows and I columns, and if the determinant of this matrix is non-zero, then Turaev said that the category is modular, and this is equivalent to asking that there are no non-trivial transparent objects. And the other example is when H is a factorizable ribbon category, factorizable algebra. Vector spaces, and factorizability is a classical notion due to Drinfeld, which tells you that a certain map between the dual of the algebra and the algebra itself is an isomorphism. And I will not state this explicitly here, but let me say that this is equivalent to asking that H mod is factorizable. So H mod is modular if and only if this Hopf algebra that we're using is factorizable in Drinfeld sense, and there are many examples of this. So if you take small quantum groups at appropriate roots of unity, or suitable for suitable roots of unity zeta. Suitable is a condition that depends on the properties of the Lie algebra you're considering. For SL2, you need to disallow multiples of 4 as the order of the root of unity. For other Lie algebra, you have more conditions, but basically you have an infinite family for every choice of the Lie algebra. You have an infinite family of the possible choices of a root of unity that will define for you a quantum group that gives you a concrete example of a factorizable Hopf algebra that gives you a concrete example of a modular category. So again, like, I don't have time, unfortunately, to provide the explicit formulas for these, but they are available. I mean, this construction is not just abstract. It comes with a bunch of concrete examples that you can use to make computations. So, okay, with a modular category, we can define TQFTs on Frey-Nietter's cubordisms, also TQFTs on Atiyah's category of cubordisms, and even on extended category, on 2 categories of cubordisms. And in order to do this, we need to use another ingredient that we have every time we have a modular category. Actually, a unimodular category is enough. And let's say that H and C is a Hopf algebra. Then form on H, which is a morphism in the category from H to the tensor unit, is said to be is called the left integral form. If it satisfies this equation, where delta and eta are the coproduct and the co-unit. So in the diagrammatic notation that I used, that I showed in slides last time, if you denote like this the integral form, then this condition is the following. I use the so, and this is a very important linear form on a Hopf algebra. There is a result due to some people, this fellow Lukashenko. And Ryan, which tells you that if C is modular, actually the result is more general. It's enough to consider unimodular, which is a notion I haven't introduced, but like in a modular category, this always holds. Is a modular, so ribbon category. And if H and C is a Hopf algebra, then there exists a unique up to non-zero scalar left integral form lambda on H. So integrals exist in unimodular ribbon categories, in particular in modular categories, which are non-degenerate example of a unimodular ribbon category. And for every Hopf algebra, they exist, and they are unique up to scalar. I mean, non-zero scalar for non-zero integrals, but in general, the zero linear form is always also an integral. And furthermore, in the special case when you take H to be the Hopf algebra that we described last time, the one provided by the end with structural morphisms obtained as the image under the functor we defined last time of the structural morphisms for the Hopf algebra structure on the functor torus on the object sigma 1 in the category of Crane-Yetter cobordisms. That one is a Hopf algebra, is kind of the universal underlying one for these constructions. Then if you take this Hopf algebra, then the left integral form is actually a two-sided, meaning that it's antipode invariant. Okay. So in axioms that I used last time, it's this kind of axiom. In the notation I used last time, it's this kind of axiom. Yes.
I think you're switching around between integral and cold.
This to me. Oh, you're right. Sorry. Yes. So here is really an integral, and here I use this. Sorry. You're right.
Also the defining property.
Yeah. The defining.
The unit and the.
You're right.
No, in the diagram in the bracket
on the right. It's like
the dotted one is on the top.
Yeah. So do you mean this?
No,
on the right
one. Yeah. Okay, that was very incoherent. Sorry, because I don't have this in my notes, so I improvised. So this is an integral, and this is what we want. Right? Thanks very much. And this is also not what I wanted. By the way, so like what I wrote, okay, so what I wrote here didn't make sense because I was mixing two things, but you have the dual notation which gives you like symmetric relations which also hold, and so I'm mixing them all up. Let me tell you what I actually wanted to tell you. This one. Okay, thanks. I'm very tired also myself. Okay, so this was just to say that we need, so basically to do the construction we need modular category of which we have many concrete examples. There exist many concrete examples. In this category, we are using this magical object, which is the end, And it's a Hopf algebra, we showed it last time. And it always admits a magical linear form, which is the left integral, which is actually a two-sided integral in this case. And what are the examples? These linear forms, these forms. If C is in modular category, and C is semi-simple, then the unique up to scalar left integral on the end, and I recall that the end in the semi-simple case is a direct sum of tensor squares of simple objects. Like the simple object tensor is dual, you take the direct sum over all simple objects up to isomorphism. This is the end, and in this case, lambda is given by this formula. So it's a row. I mean, like if you understand the direct sums as vectors of objects, then morphisms between vectors of objects, so between direct sums, can be organized into matrices of morphisms that compose exactly as matrices compose, and so you can understand a morphism from the direct sum of all the tensor squares of simple objects to one as some sort of row of morphisms in the category, one for every simple object. And these are the co-evaluation of the simple object times its categorical dimension. And this is the Kirby, this is sometimes known as the Kirby column. So in the semi-simple case, for those of you who happen to know the semi-simple construction and don't happen to know the non-semi-simple one, we recover exactly what was used by Turay. The story I'm telling is in a different language, but it contains the original one. And if C is H mod, then and if C is H mod and lambda in H star is a left integral form on H, a left integral form on H is a left integral form in this algebra in the category of vector spaces. So the definition is the same. Here I erased what I had to. This was okay. This was okay. It was here the problem. Right. A left integral form implies that the same linear form understood as an H interpoiler from the adjoint representation to the trivial representation is a two-sided integral form on H on the adjoint representation. So what was just, I mean, this is because in general, factorizable Riemann-Hopf algebras, they are always unimodular in the sense that they have an integral element which satisfies some sort of dual equation, which is two-sided, is antipode invariant as a consequence of unimodularity. But their left integral forms are not in general right integral forms too. They are not antipode invariant. So this condition here is typically not satisfied in concrete examples inside the category of vector spaces. But we've seen that there is this. So if we replace a Hopf algebra with its adjoint representation as an object in the category H modules instead of in the category vector spaces, then this is also a Hopf algebra in a braided sense, so inside a braided category, which is non-trivially braided. And what was just a left integral form becomes, in this category, a two-sided integral, meaning that it becomes antipode invariant. Yes, very good. So now here, and this is distributed to Kerner and Lubashenko, although you will not find, I think, maybe you will, but I couldn't point to you where in Kerner and Lubashenko's literature you will find exactly the statement as I'm formulating it, but they construct much more, and this is contained in there. So every modular category C a braided monoidal function. From the whole category of cobordisms, or from the whole category of Kirby tangles to C, which sends again. So which extends the one we defined last time over just top tangles. We can extend it to arbitrary Kirby tangles, to arbitrary cobordisms, in other words. But for this, you need your category to be modular, to be factored. Okay, and the sketch of the proof. So I recall to you that to define the portion of this functor that we already defined, we only used the universal property of satisfied by the end, which can be understood really in these terms. So the universal property of the end is precisely what tells you that for every top tangle there exists a unique morphism between tensor powers of the end such that every dinatural transformation factors through this morphism. And here we need something more. So not every component in a Kirby tangle is an arc component, is a top tangle component, but every Kirby tangle admits a top tangle presentation. So every Kirby tangle T from G to G prime, I call this is a tangle with G prime arc components embedded inside the genus G handle body, the standard one we fixed last time, and furthermore, next to the G prime top tangle components, you might also have some number of closed components this time. And every T like this in Kirby tangles admits a top tangle presentation. What is a top tangle presentation? Let's call it T tilde from G to G prime plus H, where H is going to be the number of closed components. This is a morphism in top tangles. What's that? Yeah, so what is a what is a top tangle presentation? It's a morphism of this form such that P is equal to, I used green, I think let me use green. Okay. So, such that we have G prime copies of the identity here, and H copies of, well, this is the integral actually in the category of components. And you compose, so a top tangle presentation is a top tangle such that, so with H additional arc components and no closed components, such that if you close the additional arc components like this, you get the original tangle. And every Kirby tangle admits such a presentation. For every closed component, you just need to choose a way to open it. You choose a point, you isotope it to the top of your diagram, and then kind of cut it off, and you get a T tilde, such that if you cap it back, you will. And the point is that these are highly non-unique. I mean, there are many choices involved in how you want to open a closed component. You choose a point, a path, a framing for the path, many things, an orientation. And the point is that all these choices are irrelevant. I mean, they will yield the same example, the same morphism if you define the morphism to be like this. So define JC of T be the identity on E tensor G prime tensor the integral tensor power H composed with what we defined last time. And you can show that is independent of T tilde. Basically, so already last time to define J on a top tangle, we made some minor choices. We chose a regular diagram, meaning that we chose a way to remove everything that was complicated inside the one handles and push it. And I didn't maybe explain this, but there is a choice involved in there too. So different regular diagrams, meaning the portions that are inside the cylinder and not in the handles. Well, different regular diagrams for the same top tangle might not be isotopic. You can make different choices, but dinaturality of the handles ensures that these choices yield the same morphism. Here you have many more choices involved in how to open, but really these choices we take care of them by using the integral to evaluate the components we open. The fact that the integral is a form is a morphism from the Hopf-Algebra to the tensor unit will tell you that it doesn't matter the path you choose to open the framing of this path, the order of the components, in which order you open them. This is all irrelevant. The fact that the antipode is that the integral is antipode invariant will tell you that also the orientation that you implicitly choose for every component in how you want to open it is irrelevant, because changing the orientation is a composition with S. And the fact that this is that the antipode, that the integral is a quantum character will tell you that it doesn't matter the point where you start isototing the component to open it up. And furthermore, the main thing is that the equation satisfied by the integral tells you that what you get at the end, well, it's not only independent of t, it's also invariant under Kirby moves. So this is the main point. It's independent of t anytime you choose a quantum character, but and invariant under frame Kirby moves. And this really uses the fact that we are working with an integral form. The equation satisfied by the integral, the defining equation for the integral, can really be understood as invariance under Kirby moves. So yes, with the time that's left, I will. So this tells you how to define the TQFT on the category of Kranjatar cobordisms. My initial goal was to finish this on Tuesday. Okay, and then today I would have told you how to compute it concretely for the two running examples. Turns out that in the semi-simple case, you don't need to go through this magic of there exists a unique morphism determined by the universal property of the end. I mean, since the integral is co-evaluation, it turns out that to compute the TQFT in the semi-simple case, you just label all the components in your diagram with simple objects. You take linear combinations over all possible choices. I mean, you need to multiply by the categorical dimension for closed components, and you don't do that for the open ones. And you just compute the Reshtikin-Ferrel factor on this, and this will give you the TQFT. So basically, no end calculus magic is needed to compute the TQFT in the semi-simple case. And in the case of H modules, so in the case of a concrete Hopf algebra in vector spaces, there is a simple algorithm to given once you've been given a curvy tangle to compute the intertwiner given by the TQFT from this top tangle. You just use elements of your Hopf algebra, you place them around important portions of the tangle, and you collect them in some way, you multiply them together, you apply the integral. There is an algorithm of this sort that really allows you to compute things very concretely. I don't have time to do this, unfortunately. So, but I mean, I can point you to where to find the algorithms if you need them, if you're interested. And also, I wanted to today tell you how to really extend this to a 3-to-1 TQFT. But I would need to introduce a few things that I don't have time to introduce. So instead of doing that, let me cheat and tell you what is the strategy for extending this. You cannot apply it as I will state it, but it can be applied once a crucial modification has been made. But the strategy to extend a TQFT like this, or even less, just an invariant of 3 manifolds, because this TQFT contains an invariant for closed 3 manifolds, and the morphisms of the object 1 in this category are kind of cobordisms from disk to disk. So from genus 0 surface to genus 0 surface. So they're not closed three manifolds, but there is a unique way of closing them up by gluing a ball to the complement. So you can understand these as, or otherwise you can embed the cylinder in a standard way in S3 and do surgery on S3 instead of doing it on just the cylinder. You will get a closed three manifold. And once you have an invariant of, so I claim that here you have an invariant of closed three manifolds. And once you have that, you can always extend it to a functor on the category of a TIA of three-dimensional cobordisms, and even on the two category of 3-to-1 cobordisms. It's just that it will not in general be a braided monoidal functor unless you ask for the right properties.
So I guess in these papers, you would see like some kind of ribbon functor, some kind of invariant of ribbon diagrams. And then I would say that that's stable under certain Kirby moves. And that produces my three-manifold invariant. So is this just an alternate way of saying the same thing, or is this like a completely kind of alternate way of
No, I would, it's not an alternate, I mean, it's not really an alternate way of saying the same things. It is morally if you also allow bicron graphs inside these tangles, and if you use the modified trace to define an invariant of closed of endomorphism of 0. And if you don't do that, what I'm going to tell will not work.
So this is like the semi-simple case, this would work.
So this is basically the invariant you have here without graphs and modified traces in the mix is degenerate. It will not extend to a TQFT.
Right, but in the semi-simple case, if I just allow...
In the semi-simple case, yes, you don't need to do anything else. But in the non-semi-simple case, you cannot use this functor over here. You need to renormalize the three-manifold invariant to get from this using modified traces, which is I would say it's a crucial ingredient in the construction, and so it's a pity I'm not talking about it. I was kind of trying to explain more the point of view from categories of cobordisms without anything inside them.
So this is essentially the Rashtikin-Turayev.
This is so Rashtikin-Turayev is the semi-simple case, and this is kind of the
well, I'll ask you later. Yeah.
So what the technique to extend an invariant to a functor is called the universal construction. It dates back to the work of Blanchet, Abeguer, McClung, and Vogel. And suppose you have a surface in the category of cobordisms, and you want to extend. So extending an invariant to a TQFT to a functor requires associating with the surface a vector space, for instance. Okay, and this time the difference is that here surfaces were connected with one boundary component, and in this case surfaces are closed and can have arbitrary numbers of connected components. So you want to extend this to a category where the tensor product is disjoint union and the braiding is symmetric. So you should consider this vector space, the free vector space generated by cobordism from empty to your surface inside your category of cobordisms. And by this notation, I mean the free vector space. So it's a huge vector space, infinite dimensional one. You need to consider another vector space, which is kind of which goes the other way. It's cobordisms from your surface to the empty. And you need to consider a pairing on these two spaces, between these two spaces. That will take, while a cobordism, a pair of cobordism, let's say, and we'll compute the invariant on their composition. So basically, you have one cobordism from empty to surface, another from surface to empty. You compose them to get closed endomorphism, and you compute the invariant given by your TQFT. Okay, your TQFT is now giving for you invariants only of connected stuff, but you can extend this multiplicatively on disjoint unions. So to a disjoint union of manifolds, you just assign the product of the invariants. And what you want is for this vector space so the space of cobordisms, so the free vector space generated by cobordisms, modulo the annihilator, so the orthogonal to the other vector space. You want to define this as your state space in the TQFT, because this definition is inherently functorial. It gives you always a functor. It always gives you a functor, and you hope for this functor to be a braided monoidal functor. Sorry, yes, a symmetric monoidal functor. Yes.
So, any kind of TQFT that you had that had the same kind of values on three manifolds would the state spaces would emit maps from your state spaces, I suppose.
Mm-hmm.
Is this the only way that you can extend down?
So basically, if you want, so this will give you a TQFT. I don't think it's the only way. This is the TQFT that is generated by cobordisms.
Yeah.
So every vector in the state space of your surface is going to be the image under the TQFT of some linear combination of cobordisms in your original category, in your source category. And all TQFTs, I mean, arbitrary TQFTs need not satisfy this. But once you have cobordism generated TQFTs, once you fix, I mean, there are some degrees of freedom you have. Once you have an invariant and you want to extend it down, you can choose, for instance, the category of cobordisms you're going to extend it on. And in fact, there is a problem here in the category I chose. So this is where I'm cheating. And there is a problem there, and there is a problem also in the invariant. So you have these, but yeah. So once you fix these choices, then it's a unique one. And if you have
there's a question.
Sure.
Sorry, I'm just confused. Where do you take the orthogonal complement of the vector space?
So I'm just modding out by the kernel, because well, first of all, that one is a huge infinite dimensional vector space, and under nice assumptions, this will become a finite dimensional one. And
okay, but there is also an orthogonal complement in the quotient, if I understand correctly.
An orthogonal complement in the quotient. An orthogonal complement to what?
Do you take the quotient by V prime orthogonal?
Yes.
So where do you take the orthogonal?
So the orthogonal with respect to this pairing.
Okay.
So you mean like these two spaces are paired together, and everything which gives you the zero map with respect to, so from V prime to K. So I mean, okay. Yes. You know, right.
With respect to the
yes, with respect to this pairing. So as I said, this is going to be by construction functorial, because to define the linear maps, you just need to group things. I mean, in this TQFT, vectors in state spaces are already cobordisms. So to define the linear maps, you just compose cobordisms and look at this. So this construction is naturally functorial. The problem is it might not be braided monoidal, and in fact, it is not as I've said it. So what you actually need to do here is to restrict to non-compact cobordisms decorated in C. So you need to admit ribbon graphs inside, and you need this invariant to be renormalized using the modified trace. This I'm hiding completely. So I haven't defined this. I haven't said how to define this, and it's a pity. Sorry, but the strategy still. I mean, it's this. So how should the definition be? How should the extension work? You should do something like this, and this in the with the appropriate definitions. So here, of course, you should also do this. You should consider this category here, and if you do this everywhere, then you will get honestly 50. And okay, and
also in the non-semisimple case, do you also need to add ribbon tangles? Do you also need to add C? Yes.
to add C
In the semisimple setting?
in the semisimple, you don't. You don't need.
Which part you don't need?
So I mean,
Also not need embedded ribbon graphs? Because I thought you needed it. But
okay. Sorry. You will need to allow ribbon graphs if right. So your point is right. So to do the universal construction, and get an extension of the original TQFT there, you need ribbon graphs inside. Then you can restrict what you get from the universal construction to the subcategory that lives in there of those cobordisms and surfaces that have no decoration on them. So basically, I'm defining a larger functor. So functor defined on a larger category. And to get the statements I wrote down on the first day, you can restrict to the category of non-compact cobordisms without decorations. But you're right. So to have something that that extends this construction, you need ribbon graphs inside. So in fact, I avoided ribbon graphs in this in these talks, but they are crucial. So it's just for the purposes of this presentation. I think I like them very much. And the idea to do a 3-to-1 is the same. So I'm going to sketch it even more. So say you have an object in the 2 category of cobordism. So a circle, yes, a bunch of circles. You want to define a linear category attached to this one manifold, and you do it kind of in the same spirit. So again here, cheating if I don't say this, you need ribbon graphs inside 3 cobordisms and surfaces. On circles, you still have no decoration, so objects are the same. But for the morphisms, you need these. And then you consider a linear category, which is freely generated by the category of cobordisms from empty to gamma. What is the free linear category generated by this? I mean, objects are the same, and morphism spaces are freely generated by morphisms in the original category. So this is a category which is not finite at all. Like morphism spaces are all infinite dimensional. And again, the idea is to quotient it using pairing. Pairing is kind of the same. This time you go to the tensor unit in the 2 category, which is finite dimensional vector spaces, and to a pair of objects you associate, well, the TQFT, the state space you get from the previous construction. Instead of an invariant, you associate the state space, and have a pair of morphisms in this category. You go to the linear map that you get by composing. Okay, and then you define your linear category to be the quotient of this category by the kernel, by the orthogonal to this pair. Okay, like the last thing I want to, and this is also natural and functorial. I have 1 minute, but let me say one last thing. So, the functor you get, so the theorem is that if C is a modular category, then this, once you appropriately complete and go to finitely complete linear categories, it becomes an TQFT. It sends gamma to the finite completion of this category. And we can really describe the image in very concrete terms. So
It's projectives, injectives.
sorry,
For the completion, it's projectives.
finite completion means what is so
Before you complete, is it projectives?
no. Before you complete, the category of the circle is still the whole category. The point is that it's not monoidal if you don't complete. Because, well, I will tell you why in a second. So then it's not projectives and it's the whole category because I've changed conventions with respect to the ones I used in my papers, if you're familiar with that result. And so in that case, non-compact meant that the cobordisms being disallowed were those with empty incoming boundary. Here I'm doing the opposite. And it results in this projectives and the whole category are kind of paired by the modified trace in a non-degenerate way. So they kind of dual to each other in this sense. So it's kind of the same construction, but here I really get the whole category. Okay, since this is braided monoidal, then this is vector spaces and S1 is sent C to the whole category C. And for instance, a pair of bands, right? This is sent to a functor from, well, up to isomorphism. This is sent to this functor. This is the functor that implements the tensor product in C up to equivalence. And with these conventions, you have access to the disk. This is the unit. And the last one I want to describe is the Okay, I could describe the pair of pens in the opposite direction, but maybe I'll just describe this one. And if you want to get the pair of pens in the opposite direction, you just compose this with this. And this is, well, the functor that sends. So this is an object, basically, in the category, and it's the end. And why do you need finite completion? Well, so basically, what I'm saying here is that this two-dimensional cobordism over here is the end, well, of this functor in this category, and you need to be able to. So if the functor is monoidal, since this category over here, the category associated with two circles, it needs to be it needs to be described in terms of two copies of the category with one circle where objects are connected, attached to each circle. You need to be able to express this element in terms of well, pairs of objects in the category of a single circle. And you can do this by, so this is the end, so this can be described as a limit, but it's not there if you don't finitely complete the category. So this equivalence is true even without this, but this thing is not if you don't complete. So completing allows you to get a monoidal functor. Okay, I stop here because I'm over time. But the moral here is that what's remarkable is that, maybe not so remarkable, because these axioms allow you to construct a TQFT, which is just is not an extended TQFT, but looks more like a slice of an extended TQFT than a standard TQFT, because it already has codimension 2 pieces. I mean, it already has corners and stuff. And indeed, you don't need any extra assumptions to extend Kerler-Lubashenko down to circles. If you want to go to points, you need extra assumptions, but in this generality, you always go down to circles, and that's all here.
Thank you very much for these very nice lectures. We have time for some questions. Yeah.
I suppose you can get something like a braided structure on C by looking at the corresponding free bordism. Do you know if this is the same braiding?
Yeah.
So do you get C as the modular category back?
Yes. So basically, well, so what you get, so, you know, like okay, I haven't explained this here, but I claimed it on the first lecture. The restriction of this construction here to Prenieter cobordisms, which are a subcategory of the category of morphisms between empty and circle, are just the connected ones. Well, if you restrict this construction to that subcategory, you really get back Kerler-Lubashenko. And Kerler-Lubashenko has target C. The braiding goes to the braiding. The tensor product goes to tensor product. So this is the tensor product. I mean, like this, and you're right. So I haven't talked about the braiding, but the braiding goes to them. Yes.
Can you say a little bit more about what this completion is? In my mind, you're Karubi completing, but I think you're not doing that.
No. So, well, to finitely complete, you need to consider the Yoneda embedding, and then consider the smallest finitely complete category inside the category of functors from.
So this would give me more morphisms, even if I start with something.
So you get more objects, for instance, in here. So if you right, so you if you do just the idempotent and additive completion, you just add the direct sums and images of idempotence. But this way you add all finite limits. For instance, you add also well, the end, which can be described as a finite limit in a finite category. It's a sub-object of a tensor product of. I mean, if you consider all the projective covers of the simple in this category, which are infinite number, and tensor them together, consider the direct sum as you do in the semi-simple case, then the end is a sub-object in there, and not, but only a sub-object. Yes, and to get it, you need this finite completion.
But I guess my confusion is that you're saying that you already have the full category. If I took the Deligne tensor product,
Yes.
I would already have that I would already have the coend in the category.
Yeah, well, yeah. So the point is, if you take the Deligne product, you already have it there. But the point is that if you don't complete this, it will not be, so it's not true that this is equivalent to this. But this is equivalent. I mean, this operation does nothing, but this makes it equivalent. So this is for monoidality.
Okay. There are no more immediate questions, and let's thank Marco again, and let's have a coffee break.